Good morning, everybody. Today we are discussing the next topic, that is asymmetric Aldol reaction. So, Aldol reaction means it is an addition of the enolate to electrophile. Usually, we are using electrophile as aldehyde or ketone. And the stereochemistry of the final product depend upon the geometry of the enolate, which is used in the chemical reaction. And as you know that the Aldol reaction create two new chiral center in a single step and a new CC sigma bond. Now we are moving into the Aldol reaction. See here in the Aldol reaction we are using a ketone and we use the LDA as the base. So LDA will pick up one of the electron which is near to the carbonyl group and easily form an enolate, and in the enolate the the ketone is added. Here the instead of ketone we are using aldehyde as PHC double bond OH. So usually we will get two product, that is the two, as we said earlier, the two chiral centers are produced and a new CC sigma bond is formed, and we will get a two product for ordinary Aldol reaction, and these two product are diastereomer. So since there are two product is formed in the Aldol reaction, this is an example for the diastereo selective reaction. So as you know that in the asymmetric synthesis, we need only one single product. For that, first of all, we are clubbing the starting material, that is for the formation of the enolate. We are first of all clubbing with the starting material with an chiral axillary. So see here, the chiral axillary, it is a heterocyclic ring which is added to a ketone, and here the base is NiPr2 minus, and it will pick up the one of the hydrogen here, and it will readily form an enolate. And since the chiral axillary is attached to the enolate, it is sterically hindered, then the aldehyde is added to the reaction center and the rearrangement will occur and a new CC sigma bond is formed. Then after the Aldol reaction we can remove the chiral axillary, thus we can generate the actual product. Now here, if we are using this example, in this example the enolate, the alkene has the two possibility to approach the enolate either from the front or from the backward. So in order to avoid this situation, we are using borane as the base. Okay, so here in the example we are actually coupled with the aldehyde with an chiral axillary, and heterocyclic ring is the chiral axillary and which is attached to a ketone group. And instead of this base, that is NiPr2 and LDA in the ordinary reaction, we are using borane as the base. Okay, here we used Bu2 twice BOTF as the base, and NeE2 is also used as a base. So these two couple will act as a base, and we will get only single product, and our alkene is the, our electrophile is the PHCHO, and LiOH and H2O and water is used for removing the chiral axillary. Now we are moving into the mechanism. See here, first of all, a heterocyclic ring which is act as a chiral axillary is coupled with our ketone, and as we said earlier, borane and Ne thrice act as a base. It will pick up one of the electron. First of all, NET thrice pick up one of the electron and it easily form an enolate, and this enolate coupled with BBU twice. We know that boranes are electron deficient. So boron atom have a vacant p orbital, and this vacant p orbital is used to form a bond with the chiral carbonyl atom. Chiral carbon. Then the carbonyl group of the chiral axillary. Then see here we will get a cis enolate which is clubbed with a boron, and boron align the two carbonyl oxygen to the same plane, and if we add an aldehyde RCHO cannot bind with the boron directly because boron have only this much. Boron has the capacity to form the 3 bond with the other atom. So boron will eliminate the bond between the carbonyl of the chiral axillary and form a new bond with the aldehyde. See here in the third structure. Then after that we know that the ketone or aldehyde, that is the electrophile, can approach the enolate only one side. This is mainly due to, see here in this example, if the boron is attached to eliminate the bond between the carbonyl of the chiral carbon and form a bond with the ketone, which is an electrophile. In order to avoid the steric hindrance between the boron of the 3 oxygen atom, one in the carbonyl of the chiral axillary, other in the enolate, and the last oxygen is from the aldehyde. So in order to avoid the steric hindrance, the chiral axillary will turn back, and see here the position of the methyl group is shifted away from the observer. Then if we add the aldehyde, it can approach only from the front side. Okay, then it form a 6-membered transition state just like this, and here the R group, see here the R group of the aldehyde is equatorial position in order to avoid the steric hindrance, and methyl has to be a pseudo axial position. See here the methyl group is in the pseudo axial position and R group is in the pseudo equatorial position. So we have to avoid the maximum steric hindrance. Then after the Aldol reaction, we can remove the chiral axillary by using water and hydrogen peroxide, and the final product is this one. And here we can see that both the methyl and the OH group are syn to each other, and we will get only one single product. And this model is known as Seemann-Klassler transition state, and this transition state is very important, and this transition state is a Seemann-Klassler transition state. So this is the chiral axillary controlled Aldol reaction. I hope that you understood the concept. Thank you.